effect and pressure gradient, and we've talked about high and low pressures across the globe. So let's put it all together, and let's talk about the general circulation model that we see on the globe. Now, in general, these are some of the things that we've seen already. Now, in general, warm air is transferred poleward and is replaced by cold air moving towards the equator. So remember, our general circulation pattern, warm air will rise from the equator and move towards the poles. Also, air that rises is associated with low pressure, whereas air that sinks is associated with high pressure. And this becomes important coming up in the next section when we start talking about weather formation. And finally, low pressure produces rain, while high pressure produces dry conditions. You can also think of it, low pressure produces not so nice weather, whereas high pressure produces pretty nice weather. Temperature irregardless, so don't think of it as low pressure is cold weather, high pressure is warm. Don't think of it like that. Think of it as like cloudy versus clear skies. So there are a couple cells that are going on across the globe where we're talking about that high air, the warm air rises and the cold air falls. And we see something called the Hadley Cell. Now this happens directly on the equator. We do have some similar cells happening across the globe, but think of this as being close to the equator. So the Hadley Cell produces sort of like a warm air rises, cold air fall convection current, and it's produced by the direct heating of the equator by the sun. So air is forced to rise by convection, and the air is going to travel to the poles, and it's going to sink at a subtropical high, that subtropical high zone that we have talked about in previous lessons. Now, the Hadley cell kind of represents what's going on in the polar cell. If you notice from this little animation that the air is rising and falling in the same general direction, it's going in a counterclockwise direction. Now, in between that, we have an indirect cell, and this is called a feral cell. Now, this is similar to the Hadley cell, it's just in reverse, and it's found in mid-latitudes and high latitudes. So if you kind of remember and kind of picture in your head some of these zones here, right here we're actually talking of probably about 30 degrees latitude, and this up here is about 60. So the feral cell happens in between, somewhere in between there. Now your Hadley cell, which is in red, is going to interlink with the mid-latitude cell, this feral cell right here. It's going to rotate it in reverse, and in turn it's going to rotate this polar cell. Think of it as gears. As this gear turns, it's going to force this gear to turn in the opposite direction. And as this gear turns, it turns that polar cell. So think of them as gears. They're all working together to redistribute the heat around Earth's globe. Now, in more detail, let's talk about that Hadley cell. And I might go back to take a look at that picture. You'll also notice that there's a picture coming forward as well. But let's take a look at the Hadley cell in detail. I sort of break it down into a little bit more detail. So this north-south flow of the Hadley cell is known as meridional flow. So what we see are easterly winds at the surface being replaced by westerly winds a little bit above it, above in the atmosphere. Now at the ITCZ, remember that intertropical convection zone, convectional storms will lift the air into the atmosphere, and this is going to increase air pressure near the tropopause. Now, winds are going to diverge at high altitude, meaning that they're going to disperse, they're going to move outwards, moving out of the equatorial regions towards the poles. Now, the winds lose heat by radiation, so in essence, the air is getting cooler. So let's just kind of take a step back and take a look at this picture for a moment. So we're at the ITCZ here. Now we have these winds kind of at the surface, easterly winds are changing into westerly winds up in the atmosphere. What we're going to have are those convergent storms, or the convection storms, lifting the air up here, and it's going to rise, and it's going to become a low pressure cell. Now these will eventually cool, and it's going to kind of move over a little bit due to all the upper air movement. It's going to become heavier, and then eventually it's going to sink. And that's about right where we are. So as they're moving towards the poles, the winds are going to lose that heat by radiation. As it loses heat, it becomes cooler. It's going to contract. It's going to get closer together. Think of yourself when you get cold. You kind of shrivel up into a little ball into your blanket. So as the air is contracting, more air can move in, and it's going to start to increase the air pressure, and that's at that subtropical high zone right there. Now, because the air is starting to increase in pressure, it's becoming heavier, and this denser air is going to sink, and it's going to cause stability. Or in further lessons, you'll actually hear the term subsidence. So as the air sinks, it's going to become more stable. So we also see things going on called Rossby waves and jet streams. So we have, first let's talk about jet streams, and then we'll talk about Rossby waves. So jet streams are strong, regular winds that blow in the upper atmosphere at about 6 miles or about 10 kilometers above the surface. A lot of times, airplanes will take the jet stream and will ride the jet stream so they can get to places faster. So these blow between the poles and the tropics, and they blow pretty much about 62 to 186 miles per hour, or in kilometers per hour, it's 100 to 300 kilometers per hour. Now there are some times where they travel faster than this, but imagine a plane riding in this and going at speed. Planes can travel pretty fast between places. This is usually why taking a plane from California to basically from the west coast to the east coast of the United States will take a shorter amount of time than traveling backwards. Now there's typically 2 jet streams in each hemisphere, and this picture is showing you those 2 jet streams. From about 30 degrees to 50 degrees latitude, both north and south, we have what's known as the polar jet, and these tend to flow eastward overall. The subtropical jet also flows pretty much eastward as well. However, it does have a very strong westward component, and we'll talk about that in a second. So our polar jets pretty much run eastward. Think about the rotation of the Earth, and that's why they go from west to east. Now between 20 degrees and 30 degrees latitude, both north and south, we do have a subtropical Dred, and this actually flows westward. I mean, again, overall it's going to flow eastward, however, according to this picture. However, if you think about some of the storm development that happens in the summer, think of our hurricanes, think of the cyclones that form in the Pacific Ocean. These actually come directly off of Africa and do travel in a westerly pattern over to the United States. So the subtropical jet, especially in the summertime in the northern hemisphere, will produce storms that travel from west to east. So when they talk about it flowing westward, yes, it actually can. Now, greater the temperature differences that we see here, the stronger the jet stream. And you'll see, especially in wintertime, we see this polar jet really dipping down into the United States, causing a lot of low pressure and cold weather. In the summertime, the subtropical jet tends to move upwards, bringing a lot of drier air, bringing a lot of higher pressure to this Midwest and the southern states here. So these 2 jets, depending upon the season, will bring in different types of weather that kind of correspond with the seasons. So the jet stream, we have 2 per hemisphere. Now, talking about Rossby waves. Rossby waves are a little bit more confusing because these are sort of like jet streams, except they're a little bit smaller. They move in much more random patterns. Rossby waves are meandering rivers of air formed by westerly winds. Now we tend to see 3 to 6 waves in each hemisphere. And in the pictures that you see down here, it looks like we have about 5 of them. There's 5 different circles. Remember, these are called isobars. Now these are formed by major relief barriers like mountains, formed by thermal differences, or formed by uneven land-sea interfaces. Now this is basically the altitude. From one land to sea interface. We have lower sea levels versus higher land levels and things like that. So an uneven surface. Now as patterns become more exaggerated, there's going to be a pinching off of this air, and you can kind of see this down here. Now normally with Rossby waves, and right here actually if you think about it, we're looking down on the North Pole. So we're looking down upon it. So here's the United States over here, kind of down towards the bottom. And over here we see Europe and Asia. So remember, we're looking down on the North Pole. These waves right here, these are our Rossby waves. Now we have picture A and B. Let's just take a look at picture B, because this is sort of the normal version minus this little part over here, this low pressure. So with Rossby waves, we see these bands or these waves of movement, of air movement kind of going around the globe. Now what's going to start to happen is, depending upon where these bands are moving, either over lands, mountains, maybe we have thermal differences, these bands will sort of look like what A is doing. We're going to start to see these extreme meanders that kind of go through. Again, depends upon what's going on. The barriers, thermal differences, land and sea interface changes. Once we have these bands sort of doing these really extreme meanders, they're going to pinch off, much like those oxbow lakes when we started talking about rivers previously. So they're going to sort of pinch themselves off, and they're going to become their own little cell. So in this case, on A, we have these extreme bands, and it's pinching off in B, it's pinching off that low pressure center right here. And so we have this pressure center, this low pressure center over the United States right now. And that's probably going to cause, depending upon the time of year, it's going to cause precipitation and cloudy skies and just icky weather in general. So our Rossby waves are kind of like jet streams. They're just at a smaller scale. And they really get bombarded due to these mountains or thermal differences. And that's how they pretty much form. So this is an overall picture of what's going on. And actually in class we are going to draw something like this, so you have it in front of you so you can kind of remember it from place to place, from test to test, whatever you're doing. So imagine a rotation, a west to east pattern. So this is our rotation right here. Now we have Hadley cells going on, and that's what these particular things are going on right above the equator. We have the Hadley cells above and below the equator. We have those feral cells that are happening right either to the bottom of the Hadley cell or to the top of the Hadley cell, depending upon which hemisphere we're in. And then at the poles we have those polar cells. So remember what happens at the Hadley cells. We have the air is going to rise at the equator due to those convection storms, and the air is going to rise, causing low pressure, and they're going to basically become colder, denser. Air is going to be allowed to move in, which rises the pressure as it's moving towards the poles, and it's going to sink, creating areas of higher pressure or areas of subsidence, stability. And again, once we're in these feral cells, we have air rising. We're going to have these areas of cloudiness that we see in the low pressure centers, and then up towards the poles we're going to have layers of higher pressure as well. So remember, we have these bands of high pressure or low pressure at the equator, then high pressure around the Tropic of Capricorn and Tropic of Cancer, and then we have areas of low pressure, and then we have areas of high pressure right at the poles. So high, low,